Okay, guys, we're back. Let's jump into the laboratory and let's think about how it is in the laboratory a researcher would go about studying whether an antibiotic is going to be effective or not against a bacterium. Antibiotic susceptibility testing has to take place in the lab well before we're going to test it on a patient, right? We're going to have to do a lot of testing before we even go to animal models to look and see if this antibiotic is going to work. So first thing I'd like to do is to go over yet a couple more terms. When it comes to the effectiveness of antimicrobials, we talk about two things a lot of times. We talk about a minimum inhibitory concentration. This came up in a previous clip. We need to achieve this thing called minimum inhibitory concentration at the site of an infection to be effective against getting rid of that infection. Okay? So what is the basic definition here? A minimum inhibitory concentration, MIC, is the lowest concentration of the antibiotic that kills and inhibits visible growth. Okay. So what this means is this is just the naked eye, right? If I add a drug into some broth, let's say, and I stick it in the incubator and I come back and I look at it and I don't see anything there, that's what minimum inhibitory concentration is. It doesn't seem very accurate, right? The fact that you would look at it and it doesn't look like there's anything there, and that this would actually be something that we're going for, but it is. Okay? We're not going for killing all of the cells that are possibly in that broth. If we're looking for minimum bactericidal concentration, bactericidal was a term we learned last time, cidal for killing, right? So minimum bactericidal concentration, this is all about killing pretty much almost all the cells, okay? The lowest concentrations, that's the minimum part, that's the minimum here, right? And up here we also saw a minimum, but here it's the inhibitory concentration, not the bactericidal concentration. So when I'm going for the minimum bactericidal concentration, here I'm going for the lowest concentration of that drug that kills pretty much 99.9% of the original bacteria we put into that broth. Okay? So we're going for the MIC. Now, why wouldn't you go for killing all of the cells? Let's say these cells are not of the type that would cause some crazy immune response if you killed them. Why would we still go for the minimum inhibitory concentration rather than bactericidal concentration? The answer would be we need to stay away from all of the other nasty effects that drugs can have. Side effects, allergies, these kinds of things, right? So the lower we can keep any particular drug concentration within the system, the less of a possibility you'll have those side effects. And almost all drugs have side effects, all right? So this is always a consideration we need to keep looking at, all right? What kind of methods are we going to use to find the minimum inhibitory concentration? Okay, there are three methods: a broth dilution test, a Kirby-Bauer disc diffusion assay, and just so you're aware, if you just see disc diffusion, it's still the same thing. Okay, a disc diffusion test or a disc diffusion assay, if it doesn't have this Kirby-Bauer in front of it, don't worry about it. Okay. And there's also something called an e-test. All of these are ways of seeking out the minimum inhibitory concentration. Okay, guys, let's look at this broth dilution test first. Okay, to do this, and it's quite easy to go about this, we could get out some test tubes, various vessels, all the same size, and we could put a medium in there, a broth, let's say, into each of those tubes. Okay, so there's nothing different in that respect. But then what we would do in the broth of each of those tubes, we would put different amounts of an antibiotic, okay? So let's say we could put in penicillin, right? That would be the drug we could study. Now, after this, we could come along, inoculate each of those tubes, stash in the incubator for a day, and come back and look at it. And we might be looking for these two concentrations that I've introduced earlier in this clip. We could look for the lowest concentration that visibly resulted in no microbial growth. It looks like there's nothing there, MIC, right? Or we could be looking for the lowest concentration, which gives us 99.9% killing. That would be hard to recover from, right? For a culture to have pretty much all the cells are dead. This would be a concentration from which the organisms would not be able to really recover very well after that drug is applied, right? So this would be the minimum bactericidal concentration. Two different concentrations we could look for as a result of doing this test. Now I think to show you, to kind of illustrate this, it's best to, let's look at an image where this experiment was done. So here, let's say we're looking at the effectiveness of different drugs to kill E. coli, okay? And we have, in this case, these are not broth tubes, they're not test tubes. But what they did is they put broth into these little plastic wells. They have dishes which have much smaller vessels there built in, and this way we don't waste as much broth and equipment and supplies like that. So here what they did was they took and they put broth in each of these wells. So let's say this one on the bottom, right? They put broth in each of those wells, and they added a drug in decreasing concentrations, the most on the left and the least on the right here. So basically over here on the left side we have the highest concentrations, and on the right side we have the lowest concentrations. And it seems to me, let's say this is 24 hours later, right? We inoculated the broth with E. coli, and we came back and we see pretty much nothing in any of these. Okay? So that's streptomycin, right? It has a certain amount of effectiveness. Now let's look at what doxycycline does, right? We prepare the vessels the same, put broth in each, add doxycycline, high concentrations on the left, low concentrations as we go across. And we inoculate with E. coli, come back a day later, see what happened. And it looks to me that we do have growth in every one. All right? Doesn't seem as effective, this doxycycline, as streptomycin. So there's the first thing that we see right off the bat. This starts to allow us to tell the difference in the effectiveness between two drugs here, right? But let's now look at this middle one, okay? This is a sulfa drug, and you probably could have guessed that because sulfa is in the name, right? So this particular sulfa drug has high concentrations over here, lower concentrations as we go across. And way over on the right here, I see growth. Visible, just naked eye, I can spot the growth. And as I go across over to the left side, I see less growth and less growth. Hardly any growth here in the second one. And then over here in the first well, I see pretty much no growth. That right there, folks, is our minimum inhibitory concentration, our MIC. The minimum concentration that will not give us visible growth, right? This isn't the minimum concentration for that because I can see something growing, right? Naked eye, still can see it. This over here is the minimum concentration of this particular drug, the sulfa drug, that results in no growth visibly when I look at it in the lab. This concentration is what I'm going for. I want to kill a lot of the cells, not 99.9%. All right? Now, there's some work left to be done here to find the MIC, the minimum inhibitory concentration, when it comes to doxycycline and streptomycin, according to just what we see here. Because it seems to me we don't have high enough concentrations to kill E. coli really much at all when it comes to doxycycline yet. We need to do some more experiments, adding more doxycycline, higher concentrations, to find this MIC, right? We'd have to go off the screen to the left to find that. Do a few more tests. Now, with streptomycin, well, it's so effective that it killed, I can see pretty much nothing here, right? And so I need to go further to the right? I need to add some tests where I add less streptomycin to see where I start to barely see growth, right? And I want to move back to the one where I don't see growth, right next to it. This is how we're going to find that minimum inhibitory concentration. All right? Now, let's say the streptomycin row here, let's say I take this whole plate, I stash it back in the incubator. So I let it grow for another week. I might find growth in some of these wells, right? And if I find growth in some of those wells a week later, I would know that these are not the minimum bactericidal concentrations, right? Because they recovered, right? It didn't kill pretty much all the cells. It left enough that we had a recovery, right? So there are a couple different concentrations we can look for. The main one we want is that MIC, because it's the one that I want to achieve in the location where I have the infection if it's the patient that we're working with. I want to keep those concentrations down so as not to have to apply a toxic dose. All right. Now let's see, what about that? That's one way, right? Where we have the broth tubes or the wells where we have broth we work with. But what about disc diffusion assays? In this case, we take different filter discs, basically a kind of a porous, like a filter paper you have in chemistry that is absorbent. And we would then impregnate, basically absorb into that paper of sorts, the concentration of the antibiotics we're working with. So different concentrations are absorbed into these paper discs, okay? And then they're placed on plates where we've put the bacteria, right? So imagine you take a Petri dish. I'll show you pictures of this in a second, but we take an agar plate and we cover it with E. coli. But before we put it in the incubator, we take these little discs with different concentrations of the drug and we put it on there. And then later we come back and we look to see, is there a zone where bacteria didn't grow around those discs? Okay? So let me show you what this looks like. So here, all of this white stuff, okay, all through here is some bacterium growing. Let's say it could be E. coli or Staph aureus or whatever. But we see here that there is a zone of killing. Okay, there's a zone where the bacteria could not grow because of the concentration of whatever drug is in that disc. Disc diffusion, the diffusion part, is this concentration of this particular drug diffused out into the porous agar on which this bacterium was placed, and the cells couldn't survive that concentration. Okay, and here you actually see the different letters, the abbreviations that stand for the drugs. Here they're not all the same drug type. A couple that I know here, this CF I think is ciprofloxacin. Chloramphenicol I think is the CL one down here. And you know, some of you that are in the hospitals now, maybe aid in hospital and you're going to nursing school, maybe you recognize some of these. I don't. Okay, I don't see these as much in the clinical setting. I would be more the guy when I was going to school and the stuff that I learned in my techniques that would be researching this stuff in the lab, right? But still very important when you get started looking at the drugs. Okay, here what you see is an e-test. This is similar to what you saw with the disc diffusion assays, where we have a certain concentration of the drug that diffuses into the agar. However, here, this strip contains lots of different concentrations of the same drug. Okay, so take this one here in the middle, and you see all of these numbers, right? All of these numbers are showing you concentrations of whatever drug is on here. Okay, and you see a bigger zone, right? If we wanted to measure this, we could. Way up here where the concentrations of the drug is high, and then the zone gets smaller and smaller and smaller as we work our way down. And then down here we find that it's pretty much right on the verge, right on the cusp, where we would see no visible growth right above this 0.064 concentration. We found our MIC. So you see how it is we would find a minimum inhibitory concentration using an e-test. Kind of like the broth test, except here it's on a plate, not in a liquid. Right? And the minimum inhibitory concentration obviously would be different depending on the drug we're working with, because drugs are not all the same. And we saw that with the broth test as well. So now I kind of skipped to this e-test. How could we find the MIC using the disc diffusion assay? Well, here we have the discs all on one plate. We have growth from some organism here covering the plate, right? We just plastered the plate with bacteria, put these discs on here. Let's say these are all, I'm just going to make up, I'm not sure what was used here, but let's say that it was penicillin, right? And penicillin is on every one of these discs, but they're in lower concentration as we move down. And you see that there's a smaller zone, right? A smaller radius to the circle that would be there as we move down, okay? This looks pretty close, whatever that concentration is, to our MIC, the minimum inhibitory concentration, where I don't see with the naked eye anything there. If I went lower with the concentrations on these discs, I wouldn't expect to see a zone, right? And I need more than that, at least the MIC concentration at the site of the infection. So these are some interesting pictures because they show the zone of killing, right? They show, and this is what you would actually be measuring if I wanted to know is this bacterium resistant or not against this drug, right? It has a certain amount of success in killing that cell. Over here we have a different drug, right? Two different drugs. It's not important what they are, just that they're different drugs right now. But I also see when these two drugs are close enough together that I see a little bit of killing here in this zone, right? Further away than I saw over here on the right. The small concentration of the drug that seeped over there in between these two zones tells us there's a synergy. See? So there is actually a multiplied effect when they put these two drugs together, and I can actually test this in a laboratory. Here we have another interesting one. It looks to me here like this particular drug is not effective at all. The organism must be resistant to some extent against that drug, and then here we have a different drug and we see that it is effective. Over here, if I had to measure the zone here on this side of this disc, it would be pretty small. On this side, I think this is a shadow over here, so we'll ignore that. But on this side, I see no zone, right? I see no zone of killing out on the right or left of this disc. And yet I see lots of killing in between these two. Now that's a synergy for you, right? Because these two drugs on the right really are really effective together and hardly effective at all by themselves. Okay, that's a real good synergy we see there. Now, all of this data, which drugs are effective against which bacteria, at what concentrations, what are their MICs, what are their MBCs, these are all tabulated and stored in a database. The National Committee for Clinical and Laboratory Standards keeps all this stuff, and it's updated all the time, right? And doctors and hospitals have access to this database, and this needs to be updated and consulted regularly to see if which drug you might want to choose to treat your patient's infections, right? So these are all just tables that are prepared, and you can access those. You don't have to memorize all this stuff, luckily, right? All right, so we'll leave it at that, guys, and we'll come back next time and we'll dive into some of the mechanisms by which these drugs kill. All right?